Hello and welcome. Today we are going to look at the composition of functions from chapter 7 in our text. And so I have a document posted for you that we are now going to talk through together. So the context that we're going to be looking at to understand the idea of composition is this one right here. And this is a pretty realistic phenomenon. This is definitely something that occurs in real life and certainly in medicine. So the context here is that we have a drug, but that drug has a side effect of raising a patient's heart rate. And so the relationship between variable Q, which stands for the amount of drug in the patient's body, and variable R, which is the patient's heart rate, is illustrated in this table right here. So you can see that the more milligrams of drug that they have in their body, the higher that their heart rate is. So certainly side effects are a real thing. Well, here's the other phenomenon though that happens. When you take a drug, certainly your body begins to metabolize it. So if a patient is given 250 milligrams of this drug, well then over time, the amount of drug left in their bloodstream will decrease. And this table shows that. So notice right when they first get the injection, they have 250 milligrams of drug in their body. But as time passes, their body is metabolizing that drug. And so the amount of milligrams is wearing off. So to help kind of preface what this is going to look like, check out this question. The medical personnel need to know that patient's heart rate as a function of time. So if it's been exactly 2 hours after that patient was given their injection, then what's their heart rate at that moment? How could we figure that out? So it's been 2 hours since I've been given my injection. So what do we know about 2 hours? Well, we know that after 2 hours, there would be 160 milligrams of that drug in my body. Okay, but the medical person needs to know what my heart rate is at that 2 hour mark. So if there's 160 milligrams in my body, then what should my heart rate be? Aha, this table up here tells me that if there's 160 milligrams of drug in the person's body, then their heart rate would be 92 beats per minute. So we can use those two tables and the relationship between these variables to conclude that after 2 hours, my heart rate should be 92 beats per minute. Okay, well now that you've kind of thought it through, how could we use those tables to fill in this table right here, which that table is going to be the patient's heart rate as a function of time. So notice the output variable here is the heart rate and the input variable here is time. So what will the patient's heart rate be after 0 hours? Well, after 0 hours, we know that they just got their injection. So they have 250 milligrams of drug in their body. And if they have 250 milligrams of drug in their body, then their heart rate should be 110. So their heart rate should be 110 beats per minute at the 0th hour. What about after 1 hour? Well, after 1 hour, 200 milligrams of drug is in the body. And if 200 milligrams of drug are in the body, then what's their heart rate? 100 beats per minute. Okay, so I want you guys to think through the rest of those numbers and see if you can make sense of what those other values will be. I'll fill in the last one for you. The last one should be 68. So if you think you can fill in the rest of those and get all the way up to the 8th hour, which at the 8th hour, your heart rate would be 68 beats per minute, then you're in business. Okay, so this concept is called composition of functions. So I'm going to share my whiteboard now so it's easier to write, but composition, where's my little, there we go. Share screen, whiteboard, come on. There we go. Okay. So composition of functions is what this concept is called. And composition of functions, in its most like simplest definition, is simply when the output of one function becomes the input of another function. So when the output of one function becomes the input of another function. So let's think back to that example that we just did. And let's see how that definition applies. So how did we go through this series of questions? How did we answer this series of questions? So if you recall, let's just go back to this question, the 2-hour mark. So how did we figure out the 2-hour mark? Well, we had to look at this table first, because this table is the one that inputs time and outputs the drug level, Q. So by going to that table, we were able to see that after 2 hours, there would be 160 milligrams of drug. The output is 160 milligrams of drug. But that's not where the problem stopped. We then had to take that 160 milligrams and go look at this table for the 160 milligram mark. Well, guys, do you realize when you did this, your eyeballs had to jump to that top line in the table, the top row? So do you realize that in this particular table, the input is the drug level and the output is the heart rate? The output of this table, Q, was the input of that table. There you go. You totally did a composition when you read those tables. You had to look at the Q of T function first, input T, output Q. Okay, now you're holding the output of Q in your hands, but then you take that Q and you plug it back in to the first table. So you totally did a composition of functions when your eyeballs took you through that process. Now, let me go back to my whiteboard. Stop. There we go. Whiteboard. Okay, so as far as notation is concerned, what this is going to look like notationally speaking, it's going to say f of, but then here's where the composition comes in, g of x. So you know, normally function notation just says like f of x or f of t. Well, notice this time your input inside the parentheses, your input to that function named f is actually a whole other function that has his own input and output, input x, output g. So you're not just plugging in one thing to this function called f, that one thing is actually the result of this other creature, the other creature named g. Now, how you approach these though, you pretty much work your way, notationally speaking, from the inside out. So you start by plugging in whatever x is. X is your original input, just like kind of regular function notation has taught us that x is our input. So x gets plugged into, well, notationally speaking, x gets plugged in to g. you can see that notationally speaking, the x has to go into the function called g. So x is definitely the input to the function named g. And then, you get whatever answer you get. But then that number, whatever that number is, then becomes the new input. So whatever this answer is, then becomes the new input to the function named f. And then whatever you get out of that, well, that's your final answer. So notationally speaking, you work the notation from the inside out. So if we go look at how that would apply to the problem that we were just looking at. So look down here, number 1, evaluate R of Q of 5. R of Q of 5. So notationally speaking, I'm not going to be able to get all my things on one screen here, so bear with me, but notationally speaking, R of Q of 5, notice how I'm saying that. The function notation is the word of. So R of Q of 5, notationally speaking, says that first 5 gets plugged in to the function named Q. Input to Q. So which function up here is named Q? Is it the top table or the bottom table? Well, remember that notationally speaking, the input always goes inside the parentheses. So this function is called R of Q. Oops, I don't have my little annotation. Where is it? Here it is. So this function up here, input Q, output R, that would be R. Why is this not going? Hello? Technology drama. Okay. Yes, let's try again. R of Q, there we go. Okay, so input Q, output R, so R of Q. On this one, input time, output Q, so Q of T. So which one of those notations fits what I'm trying to do? And that is to figure out what 5 gets plugged into the function named Q. R of Q of 5, R of Q of 5, R of Q of 5. That would be R of Q of 5. This one. This is the only table that tells me that I can do Q of 5. That notation right there would be Q of 5, and that's what I need is Q of 5. So I know that I have to go to that table first. So if I get this realigned, there we go. I have to use this table as my first table because notationally speaking, that's where Q of 5 comes from. Okay, so what is Q of 5? Well, it's 82. So as far as where we'd be so far, R of 5 is 82. Okay, but that's not where the notation stops. So now this is where, if you look at the notation again, so if Q of 5 is 82, okay, fine, but then that has to now get plugged in to the function named R. Now that we know 82 is the output for Q, that now has to get plugged in to the function named R. So notationally speaking, which function is named R? This guy right here, the R of Q. This formula right here says, okay, now that you know the Q value is 82, you can plug that in to this function right here, whose name is R. So what's R of 82? It is 76. And so the final answer, if you will, would be, what did I say? 76. 76. Which of course, what does that end up meaning? So, oops. There we go. So 76. And what does that mean? It means that our heart rate is 76 beats per minute. Beats per minute. Wow, that did not. Let's try that again, shall we? There we go. Beats per minute. Beats per minute. There we go. So the heart rate is 76 beats per minute after 5 hours of taking the drug. Now, notice I am not mentioning the 82 in my English sentence, and that is because you don't have to. So the 82 is what I refer to as the middleman. It's not the input, because the input was 5. It's not the final answer, because the final answer is 76. 82 is just that compositional middleman. He's like the stepping stone to get from point A to point C, since a composition is kind of like a flowchart thought process. But it's not technically the input nor the output of the final answer. So you don't have to mention the 82. Now, if you did mention the 82, that wouldn't be bad, like it wouldn't be wrong. It's just not necessary. And then just to make sure that the notation makes sense, check out this next one, number 1, part B. What is wrong with the statement Q of R of T? So notationally speaking, we'd have to start with R of T. Well, first and foremost, look at the functions that we had to begin with. There was no R of T, so that's already problematic. And then if you say to yourself, well, wait a second, Bishop, this very last table at the end though, this very last one right here, that actually would have been R of T. So maybe that's where I'm supposed to go first. Maybe that's where this problem starts. Okay, I'm willing to humor you on this one. Maybe that is where it starts. But then check it out. So you plug T into that formula and the output would have been R. And then you're supposed to take that R and plug it back in to the formula named Q. Okay, but wait a second. The only formula named Q is right here. And according to the notation of that, does that formula allow for you to input R? Does that function say, hi, I'm the function Q, and I accept inputs of R? No. For that function to work, it has to be the drug as a function of time. It's not the drug as a function of heart rate. That's not a valid function. So this, even if you tried to say, well, R of T sort of is real. It's right here. Look, it's real. Okay, maybe. But you can't then contextually say that you could take that answer, which once again is heart rate, and plug it into the formula for Q. There is no such formula named Q that accepts heart rate as its input. So this is simply not possible. You cannot input heart rate into the Q function. There is no Q of R. Not possible. So when it's a word problem like that, you really do have to be careful that contextually it makes sense. I mean, you could just start plucking numbers off of trees and making it work, but if it's not contextually sound, then it wouldn't make any sense to do so. So you definitely have to be careful. That's the one thing about compositions that can sometimes be troublesome. Okay, so now that we've kind of hashed out just like what composition means and all that jazz, let's go look at a couple of examples now. So on this one, you're doing a couple of numeric compositions, and then this one on the end, part C, is what we call a generic composition. So for this first one, well, first of all, let me just point out that you have 4 functions. You've got f of x, g of x, h of x, and t of x. This is not a word problem, so we don't have to worry about it contextually lining up. All we have to do is look at the notation and acknowledge how like the flow chart is going to go. So for part A, You start with the innermost quantity, and that guy right there gets plugged in to the function of closest proximity. So you're going to plug it into G. So you're going to input 3 to G. So what would that even mean? Well, here's G. So if I input 3 to that function, G of 3 is 3 minus 1, which is 2. So if I plug 3 into G, I get 2. That's my answer. Done. Well, not done, because now, compositionally speaking, you then take that answer, go back to your notation, take that answer and plug it in to H. So take this 2 and plug it in to H. So where's H? Here's H. So you have to plug, what is that, 2 gets plugged in to H. So what is H of 2? H of 2 is 3 times 2 squared plus 5. Let's see, 2 squared is 4. 4 times 3 is 12, plus 5 is 17. And that is the final answer. So notationally speaking, H of G of 3 is 17. You can just leave it in flowchart form, doesn't matter to me, or you can write it notationally as I did at the end. H of G of 3 is 17. Okay, now for this next one, I'm not gonna use the flowchart as my way of showing work. I'm gonna use another method, which you might like better. It's totally up to you which one you choose. So I'll show you this other way of notationally writing it. So first of all, same as before, just acknowledge that 16 gets plugged into the function named t. So what is t of 16? Well, here's my formula called t, and I now have to plug 16 into that. So t of 16 is the square root of 16 plus 3, which is the square root of 19. Now, if you really wanted to get a decimal for that, you could. The square root of 19 is 4 point something. Let's see, if you really wanted to, square root of 19, square root 19 is 4.36. So if you wanted to write it as 4.36, you could. But either way, t of 16 is root 19. But then you have to take that answer and plug it in to G. So you're going to take the 19 and you're going to plug it into G. So what is G of root 19? Well, function G is right here. So I'm going to plug root 19 into that. So it's going to say root 19 minus 1. And again, if you wanted to grab a decimal or a calculator and get the decimal approximation for this, root 19 we said was 4.36. So 4.36 minus 1 is 3.36. And that's it. That's the answer. So if you like kind of the setup of the flow chart, you can use the flow chart. If you like just the function notation setup where you just plug the number in, get your answer, but then take that answer, whoop, plug it back in again, whatever works, okay? And then there's this last one. Okay, so f of t of x, and I'm gonna write down what f was. So f is x squared, f of x is x squared, and t is the root x plus 3. Okay, so f of t of x. F of t of x. Okay. So f of t of x. And f of x has been defined as x squared, and t of x has been defined as the root of x plus 3. All right, so on this one, notice you're not plugging in any numbers. If you're not doing a numeric composition, this one is what we call a generic composition. Numerics, you plug in numbers. Generic, you just leave the variables intact. So if you think about it in a flowchart sense, you're taking x and you're plugging it into the function called t. Okay, so here's the function called t. Plug an x in. You're like, Bishop, don't you just get the same thing back? Yes, yes you do. So if you plug x into t of x, you're like, I have the formula. Yes, but then the composition really kicks in because you're not just acknowledging t of x, you're then taking that whole function, variables and everything, and you're now going to plug it in to the function called f. So here's your function called f. See how right now there's an x? Well, what you're going to plug in for x is this whole thing. This whole thing is going to go right there. So when you do that, you've got the square root of x plus 3, but then thanks to f's function, that would get squared. F's function says x squared, except now x isn't an x, it's this whole thing. You're replacing the variable with this entire other function. So you can simplify this just a touch. Squares and square roots, those are inverse operations. They undo each other, they are inverses. And so this simplifies to just be x plus 3. So what is f of t of x? It is x plus 3. That's the final answer when you compose those two functions. Okay, very good. If you need a break, now's a good time to take a break. But I'm going to keep going, so you can pause this video if you want to. But I'm going to keep on moving. And let's see what is next on the agenda. Okay, so the next item up for bids is being able to look at a function and acknowledge its composed counterparts. So if you look at this first one, first of all, the directions, let's just make sure you understand the directions. So decompose, okay, essentially means take apart. So instead of putting two functions together, this time they're already together and you're gonna separate them back out. So the following functions have two counterparts, f and g, and those two counterparts came together to make what you see here, and that is h. So this dude's name is h, but h is really the composition of two other creatures named f and g. So the way that I always think about these, and of course if we were in person right now, I'd be having you wrestle with this and trial and error, and it'd be so much fun. But alas, here we are online. And so the way that I like to think about these is there's always the broad view of the function, and then there's like the nitty-gritty pieces of the function. So like, here's what I mean. When I just glance at part A, I'm like, oh, that's a root. It's a root function. And it is a root function. And then when I get down to the nitty gritty, I'm like, oh, but it's not just any old root, it's the root of x plus 5. X plus 5 are like its inner workings. And so if you can acknowledge on a broad scale what the broad function is, that is always part of one of your formulas. The outermost function is like the broad view, and then the innermost function are like the nuts and bolts and bits and pieces. So on this one, they've asked us to name the broad view function as f. Let me get my little pen here so you can see. So they've asked us to name the outermost function as f. And so that's always the outer view of the formulas. So I'm thinking that my f function has something to do with a root. And I'm thinking that my inner function which they asked me to name him G. I'm thinking that my inner function, oops, I lost my draw tool. Here we go. My inner function has something to do with the x plus 5. Okay, well, here's the thing though. All functions, by definition, they have to have an input and output. So I can't just say a square root symbol with nothing in it. What would I ever plug into that? There's not even a variable. So even though the outermost function is a root function, because it is, you still have to acknowledge that to even have a function at all, you still need an input of sorts. So an outer function can't just be a radical symbol. You have to still think of it as inputs and outputs. So it's the radical of just x. Now, when you look closer though, you're like, oh, but it's not just an x, it's an x plus 5. And that's where the composition comes in. Because now if you go back and look at this notation says that you would take G and you would plug it in to F. Well, if I take G and plug it in right there, would I indeed get the square root of x plus 5? Yes, I would. So those are the correct two functions. F is the square root function and G is the x plus 5 function. Those are the correct decomposed counterparts. And then for part B, same thing. When I just glancing at part B, I see a quadratic. It's definitely quadratic. But when I look more nitty gritty, I'm like, oh, but it's not just a quadratic. It's got the x minus 2 in there, and of course the 3 and the minus 1, and I don't even know how this is going to work. So you can kind of play with it a little bit, but, and sometimes there's more than one right answer. I don't think there is on this one. I'll have to think about it. There might be. But the outermost, the broad view, definitely has to have something squared. It's definitely quadratic. Whereas the nuts and bolts, you're like, well, how am I going to handle this? How am I going to make sure that everything that I want is in place? And a couple things. You can do a little bit of trial and error. I mean, truly, that's one of the strategies that I would encourage you to do. But if you think about it, if you have your g of x function to be, I don't know, 3x minus 1. So maybe you're like, okay, broad view, it's quadratic. Nitty gritty, I need a 3 and a 1. I'm just making stuff up right now. Okay, well, think about it. If you take all of that and put it right there, is it going to say what you want it to say? Is it going to say 3 times the quantity of x minus 2 squared take away 1? No, not at all. Not at all. So you're like, okay, well, that didn't work. So you just kind of think about it again and you're like, well, oops, not clear, just the eraser. There we go. So then you think about it again, oops. And you're like, all right, well, maybe the 3 is supposed to be there. Maybe the 3 should already be there. And all I need to do is have the minus 2 and the minus 1. So again, I'm just playing around. Maybe this guy should take care of the minus 2 and the minus 1. Okay, you have to be careful because again, by definition of composition, you're going to take all of this and you would slip it in right there, which would technically say 3 times x minus 2 minus 1 quantity squared. That's what that would look like. If you have the minus 1 in your g function, then minus 1 would get plugged inside the square. And you're like, no, I don't want that. I don't want the minus 1 inside the square. Okay, well then that means the minus 1 wasn't composed. If you don't want the minus 1 on the inside, then you don't want the minus 1 getting composed. So that didn't work either. All right, so then you go back to the drawing board and you're like, well, gosh, maybe all of that, oops. Maybe all of that is the broad view, and all I need for my little nitty-gritty peek inside is x minus 2. Well, let's just try it. So if you compose this now, if you take g of x and plug it in right there, would it say what you want it to say? Well, you'd have 3 on the outside. It is not x squared anymore because you're composing x minus 2. So in place of the x goes the x minus 2. It's still squared. And minus 1 was on the outside now. See how that's different? Since I took the minus 1 off of the g of x and put it into the f of x instead, I'm now not plugging 1 in to the x's position. It's still just on the outside. So is that what you wanted? Yes, it is. So you really just kind of have to think about, in compositions, x is what gets replaced. The 3 does not get replaced. The 1 does not get replaced. The 2 or the squares, they don't get replaced. The variable gets replaced. So you have to ask yourself, where could I strategically put my variable and what else should be around it so that when I replace that variable with this other creature named g, it will have the structure that I want it to have. Now I know trial and error is not a student's favorite option, but on these, you just kind of have to play with it. It takes a little bit of practice, and you just kind of have to play with it to see how it works out, okay? All right. And then last but not least, so this one, number 4, you're gonna do that one on your own, and you're gonna submit proof of completing that on your own as your like attempt to make sense of it without me talking you through it. You've got the functions right there, you've got some notation. So that's gonna be yours to submit, and I'll give you feedback on it. So the last ones that I want us to do today are the table at the bottom. So the table at the bottom really is just a nice review over function notation and all of the fun stuff that comes with function notation. So I get rid of, that didn't work. Oh well, okay. So notice you've got 2 tables here. One of the tables, you input x, you output f. The other table, you input x, you output g. So there's a function called f, a function called g. And then notationally speaking, we've got compositions and even inverses just for fun. Compositions and inverses. So when you read this notation, once again, composition, you work your way from the inside, nested inside, and then work your way out. So I see a -1 and it's in parentheses, and it's the input of the function named g. Okay, so first of all, since I'm inputting to the function named g, which table should I even be looking at? The table with f of x or the table with g of x? Definitely g of x. So my focus is right here for now. Input x, output g. But notationally speaking, -1 is the input of g. So where am I looking for the -1 right now? If -1 is the input. Ta-da! -1 is the input of the function named g. Okay, so fine, his answer is -2. So this intermittent answer is -2. Okay, but it's composition. So now that you know that, oh, what is that? Weird. What is that? Get out. Bizarre. Okay. Now that you know that when you input -1 to g, you get -2, okay, fine. But now you have to take that -2, that answer gets plugged in to the function named f. So -2 now has to get plugged in to the function named f. So which table has a function named f? This one, inputs and outputs. And once again, you're looking to plug -2 into the function named f, into the function named f. So -2 for the input is right here. And so the answer is 3. So the final answer is 3. Okay, I'm going to skip down to part C because then these last ones have inverses in them too. So for part C, I'm going to grab my green colors because I see a letter G everywhere. So with my green, so for my composition, I'm starting by plugging 1 in to G. So I'm going over to my function named G and all my green marks. I'm looking for an input of 1 and I'm plugging it into the function named G. What do I get? I get -1. So the middleman, so to speak, is -1. However, it doesn't stop there because you then take that answer and you plug it back in. Okay, so here's where you have to really pay attention to the definition of composition. Right now, where did I get -1 from? I got it from right here. And right now, I am circling an output. -1 is the output. Yes, it is. However, for composition purposes though, I am now going to turn around and I'm going to use that -1 as an input of -1. The output of one function becomes the input to the next. So even though this -1 is in the output column, for composition purposes, I'm now going to turn around and look for it as an input, which is right here. And so the final answer is -2. So G of 1 is -2. Okay, and then last but not least, I'm going to do part B, and then you guys are going to do part D, and you'll submit it, and I'll see if you got it right. So for part B, what do we have? I'm going to start with my green marker because the first thing I see is G of 2. There's nothing fancy, nothing weird or inverted about that. So G of 2 means I'm going to use 2 as the input for G. So here's my input column. I'm looking for the number 2. Found it. So if I plug 2 into G, I get 1. The answer is 1. Okay, but now comes composition. So even though the answer is 1, I am now going to turn around and I'm going to use that 1. So take that whole answer and plug it in to this creature. Okay, check it out. I need to plug it in to the inverse. That is what that notation says. In to the inverse. Okay, look at my 2 tables. Are either one of those 2 tables called inverse F? No, neither one of those tables is called inverse F. Now, of course, I do have a table called F, but you're like, his name is just F though, it's not F inverse. I know, but that's where, come all the way back to January with me, that's where you have to apply the reversibility. If 1 is the input of the inverse, then doesn't that also mean that it's the output of the original? Yes, it does. The whole definition of inverses is that the inputs and the outputs are reversed. So if you're trying to find the input on the inverse, well, otherwise known as the output of the original. So where should we be looking for the number 1 right now? The output of the original. The output of the original. Can you find the number 1 in this column? Yes. And who does it pair with? -1. The answer is -1. So when you have inverse notation, but you're looking at your options and you're like, nothing is called inverse. Okay, well, you have to just apply the reversibility where the inputs and the outputs reverse, and then you can still answer the question, hopefully. So I'm going to purposefully leave part D alone and let you try that one. So your job will be to do this word problem up here and part D as proof that not only you played along with me here and took notes, but that it's making at least a little bit of sense. So thank you for your time, and let me know if you have any questions. You know where to find me, and I will talk to you guys soon. Thank you so much.